Okay, so last time we met, oops, let's try a button over here. So last time we met, we watched a couple of 20-minute videos about flight instruments. So today, and I said you didn't have to take notes, so there's no test, correction, there's no quiz today, because we didn't take notes yesterday. But that will be not the same tomorrow, because we're going to take lots of notes today. So we're going to dive right into flight instruments. Here we go. The first thing is we need to cover some basics about the Earth's atmosphere. The pressure of the atmosphere is 14.7 pounds per square inch at sea level. That is, if you took a 1 square inch column of air and went all the way up to the top of the atmosphere, the weight of that air would be 14.7 pounds if this square down here was 1 inch by 1 inch. So if you have a pressure gauge, anybody ever look at a pressure gauge for a tire, and you look at the tire pressure gauge before you hook it up to the tire, does it say 14.7? No, it says 0. It's because that gauge is telling you how much above atmospheric pressure it is. So it's sort of balanced. It's saying, okay, on one side I got atmospheric pressure, how much is inside the tire that's greater than that? Because technically, if you jack up a car and take out the valve stem, there's still 14.7 psi inside that tire. It's just on the outside of the tire is also 14.7 psi. So you need to understand that that's a very basic number, 14.7 psi. I think that's interesting because that's also stoichiometric ratio. Another way to call that is the same as 29.92 inches of mercury. And in Greek, I think it's Greek, Hg is the symbol for mercury. If you look on a periodic table of elements, mercury is symbolized by the letters capital H, lowercase g. So if you had a column of mercury, and it was sitting in a tub of mercury, and you filled it full of mercury and put your thumb on the top and then stuck the tube in upside down, and the top is sealed, the height from the top of the mercury here all the way up to wherever the mercury is floating in there, that height right there would be 29.92 inches. Because, interestingly enough, if this was a cubic inch or a square tube that was 1 inch by 1 inch, the height, the weight of this mercury in there would be 14.7 pounds, because the air pressure on the side is pushing down at 14.7 psi. Did I lose anybody there? No? All right, let's talk about density. I can erase all my little things there. If we took a cubic foot of air, and you guys are it might be a good idea to draw some of these pictures just so it'll help out. And this was 1 foot by 1 foot by 1 foot. So this is 1 cubic foot, and that's volume. If we took 1 cubic foot of volume at sea level, I'm going to make up a number, I don't know what it is. Let's just say it weighs 1/10 of a pound. We'll just say it weighs 1/10 of a pound. And we have a box, and it's made out of steel, but we drill a few holes in it here and there. So air can go in, and air can go out. And we raise this cubic foot of air, we glue it to the side of an airplane, and we fly 18,000 feet. There's less pressure at 18,000 feet. So the pressure inside of the box, which at sea level was 14.7 psi, it's going to push some of the air molecules out through those holes. Interestingly enough, at 18,000 feet, the pressure is about half. About half of the atmosphere is below you, and about half of the atmosphere is above you at 18,000 feet. So what do you think the pressure is inside of the box if we let air go in and out, if that box is at 18,000 feet? Half of the air is below us, half of the air is above us. At 18,000 feet, how much air pressure you think is in there? I know this is tough. How much, half of what? Yes. Half of 14.7, yeah. Half of the atmosphere is below us, so that's not pushing anymore. We've only got the top half of the atmosphere. So if it was at sea level and we were getting 14.7 psi and we went halfway up in the atmosphere, not halfway in distance, just halfway up in pressure, it'd be half of 14.7, so it'd be 7.35. So now, as we were climbing up to 18,000 feet, the molecules of air inside this box, did more molecules go into the box, or did more molecules leave the box? Or did the same molecules stay in the box and no molecules went in and none went out? Remember, we've got 4 holes drilled in the side. The air can do whatever it wants. Say that again? Yes, leave. Molecules will leave the box. And in fact, how many air molecules will leave the box? If we take this 18,000 feet, pressure is half of what it is at sea level. Molecules will have left the inside of the box. Half of them. Okay, now more than one person is saying the answer. Thank you. Okay. So, is the volume of the inside of this box, is it still 1 cubic foot? That's a big, thick steel box, so the volume is still the same, and we got holes drilled in the side, so nothing's pushing the box sides in and out. But there's half as many molecules in it as there was before. If at sea level we had 1/10 of a pound of molecules in it, took it up to 18,000 feet, how many pounds of molecules of air are inside it now if half of them left the box? A half of a tenth, or a 20th. Don't worry about doing the math here. I just want you to realize that that same cubic foot of air, it's not all there anymore. It doesn't weigh as much. And density is a measurement of how much does something weigh versus what volume it's in. So this has half as much weight, half as dense. What that means is if we go up in altitude, the air gets less dense. And if you don't write that down, you're silly. The higher we go in altitude, the air gets less dense because the air is allowed to expand and we have less air for any volume. As we go up in altitude, not only does the pressure get less, as we go up in altitude, the air gets less. So just for fun, if we have an airplane engine at sea level, let's say it's that Cessna that 152 out there, I think it puts out 100 horsepower. If it puts out 100 horsepower at sea level, and it's sucking in a volume of air at 14.7 psi, and it's sucking in 1/10 of a pound every Cessna 152, and we climb all the way to 18,000 feet, which would be very difficult in that airplane. We'd have to get a pilot pounds, and we'd have to put rockets on it to get it up there. But let's say we got it to 18,000 feet, and the engine is still running. How much air is going into the engine in wet molecules as compared to sea level? Half as much, yes. So what are we going to have to do at altitude? I know we're all expert pilots now operating airplane engines. If we go up in altitude, there's less air, but the carburetor is measuring volume. It's still pulling in a cubic foot of air every second or whatever it is. The carburetor is going to be doing what to the fuel? What's that? It's going to be, well, the carburetor is not going to do the burning. That's going to happen inside of the engine with the spark plugs. What's that? The carburetor is going to be taking in air, but it's volume of air and then puts in a certain amount of fuel. But if we're at 18,000 feet, we're pulling in the same volume. Go ahead. Yeah, it's going to be running ridiculously rich. Because now if we're bringing in the same volume of air, but there's only half as many molecules inside of that volume. But it's going to be shoving in fuel like we still had that 1/10 of a pound, but we're really only getting a 20th of a pound of air in. you would have to lean it. And of course, if you were flying the airplane, you would slowly probably lean it every 1,000 or 2,000 feet as you climbed. You'd pull the mixture control out. And once at 152 is never going to get to 18,000 feet. But I'm trying to get to a point here, and I'm almost there. So if we did lean it out correctly, half as much air going through the same volume, but half as much weight, and we lean it out, what fuel is going into the engine? We leaned it out, so now the carburetor's putting in half as much of the fuel as it was before. So at 18,000 feet, if we've leaned it out correctly, that engine, it doesn't have a supercharger, it doesn't have a turbocharger on it. At 18,000 feet, if it's pulling in half as many molecules of air, and where the carburetor is adjusted correctly with the red mixture control knob, and it's bringing in half as much fuel. I know this is a hard one, don't say it out loud. How much horsepower is the engine making now? If it made 100, don't say the answer out loud. If it made 100 horsepower at sea level, how much horsepower is it generating now at 18,000 feet if we did everything right? Don't say the answer out loud. We're bringing in half as many air molecules in, and half as much fuel that the engine is only burning half as much fuel as it was at sea level. Good time to raise your hand. I won't harass you very much. If the answer you're thinking of is half the horsepower, you were doing pretty good. Okay, it's because the air is less dense. So we're going to talk about a thing called density altitude. So one could argue if what I said, based on what I've told you so far, the density altitude at 18,000 feet is 18,000 feet. So we could go to the operating handbook. How much horsepower will the engine produce at 18,000 feet, and how fast will the airplane go? Although that airplane speed than it would have before. So we're going to talk about density altitude on more than one occasion. All right. So temperature. On the planet, there's a thing called standard temperature. Whoops. Standard temperature. On the surface of the Earth, on a standard day at sea level, on a standard day, ooh, there it is right there. The pressure is 14.7 psi, which is the same as 29.92 inches of mercury, which you already covered. However, the standard temperature is 15 degrees Celsius, which is the same as 59 degrees Fahrenheit. And there's about 3 or 4 Celsius to Fahrenheits that I know off the top of my head. I know that 0 degrees Celsius is the freezing point of water. That's 32 degrees Fahrenheit. I also know that 70 degrees Fahrenheit, you don't have to write these numbers down, but those on this board, 70 degrees Fahrenheit, which is a lot of people set the air conditioning in their house, is 21 degrees Celsius. I also know that 98 Fahrenheit, which is the typical of a human, is 37 degrees Celsius. And I also happen to know that minus 40 was minus 40 Celsius. So that's one place where those two temperature scales hit. So the problem is you're going to see in aviation a lot of Fahrenheit and a lot of Celsius. So you're going to have to make sure you know which one it is. If I asked you on a test, what's the standard day temperature at sea level, and you wrote 15, you wouldn't get it right unless you put a capital C after it. Does that make sense? Or you put 59, if you didn't label it, I'm automatically going to think you don't know the difference between Celsius and Fahrenheit. You won't get it wrong. It'd be 59 Fahrenheit. Now, this standard lapse rate for temperature is every 1,000 feet of altitude, it goes down minus 2 degrees Celsius. So if we went all the way up to 10,000 feet, and we started at 15 degrees Celsius, and every time we went up 1,000 feet, it went down by 2 degrees. And we do this, bang, 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 10 times. What would be the temperature if we had a standard temperature lapse rate. Let's see, if we changed 10,000 feet, and it was 2 degrees Celsius per 1,000, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Right, so it would be 20 degrees colder. We'd be at minus 5 degrees Celsius here at 10,000 feet. That's 5 Celsius below freezing. So that's probably only going to be like 26 or 27 degrees Fahrenheit. But the standard temperature lapse rate, we're only going to talk about it in Celsius because it's really nice. And interestingly enough, this standard, you don't have to write this down, but this standard temperature lapse rate, now this is average. It's not everywhere in the world on every day. But if you look at the world average, this is good up to about 60 or 70,000 feet. It's only off by 1 degree. It's that good of a rule of thumb. The other lapse rate is the pressure. If we look at an altimeter, and you might not remember from yesterday, but there's usually a knob down here, and there's a window and a needle. And when you spin this knob, the numbers and letters in here move. If you set it to 29.92 and you're at sea level and it's a standard day, the altimeter will show 0 feet. If we climb 1,000 feet, the outside air pressure won't be 29.92 anymore. We're not going to move that on the altimeter, but you lose about an inch of mercury of pressure every 1,000 feet. So if we're on the surface of the Earth and the pressure here is 29.92 and we go to 1,000 feet, the pressure is 28.92, and we go to 2,000 feet and the pressure is 27.92. This is pretty good up to about 15,000 feet. I bet you could tell me if we went all the way up to 10,000 feet, what would be the atmospheric pressure approximately? It's 1 inch of mercury for every 1,000 feet. So if we're at 0 feet above sea level, is 29.92. The question is, what if we're at 10,000 feet above sea level? Yeah, it'd be 19.92 because we'd be 29.92. And we're 10,000 feet difference. 10 times 1 inch per 1,000 is 10. Now we don't change this number on the Colesman window of the altimeter. What changes is this needle spins around and around and around, and this needle would have spun around 10 times. So there's not just a standard lapse rate of temperature as you go up, which works out into the tens and tens and tens of thousands. This standard pressure lapse rate, it works good up to about 15,000 feet. I think at 15,000 feet it's really only 800. But we're pilots and we like rules of thumb and we like averages and we like things that are typical, and so we don't have to do too much math. The reason I put this in here about changes is because we can talk about a standard temperature lapse rate, a standard pressure lapse rate. We can talk about at 18,000 feet, half the air is below you and half of it is above you. But that's just on an average day. How many days are average? Not that many. So here at Reedley International Airport, it's 380 some feet above sea level. So that's not even 1,000. So, but let's just, it's close to 0 than it is 1,000, right? Or colder than Celsius. 80 is about 1/3 of the way to 1,000. So it ought to be about 1/3 of the way to 2 degrees colder. That's 0.7 degrees. So it ought to be 15 degrees minus 0.7 at Reedley. So that's 14.3 Celsius. That's about 60 degrees. Do you think it's 60 degrees at Reedley Airport right now? No, we're away from summer. Probably 90 something. It's cooler than it's been for the last couple of months. So is it a standard temperature at Reedley Airport today? No. In fact, we could probably go out there with an altimeter and find out that it's probably not a standard pressure either. The reason I'm telling you about these changes is, as a pilot, you're going to have to take into account these non-standard pressures and these non-standard temperatures, so you set your altimeter correctly, so you can estimate performance of the aircraft. So let's say it's a really hot day, for instance. The speed of a molecule of air bouncing around when the molecule gets warmer. Does it bounce around faster or slower? Okay, faster. So if it bounces around faster, hold it, increase the pressure in there. But if there's holes drilled in it, like here in the atmosphere, it's not constricted, the air will tend to expand. Well, if the air expands, that means it's and remember, only air. Can't pull in as many molecules. If we lean the engine correctly, it can't pull. So on a hotter than standard day, the engine won't produce as much horsepower. So there's actually a table, a chart in the Pilot Operating Handbook where you enter it with what's the altitude of the airport and what's the temperature, and then if you're load the airplane up to maximum, how long of a runway do you need before you can get off the ground? Tell you how long do you need before you can clear a 50-foot obstacle and not hit that tree or that fence at the end of the runway. But tomorrow, at the same exact airport, it'll be a different temperature and it'll be a different pressure. So every time you go flying, you're going to have to figure this stuff out. So understanding all this stuff will help you be able to do that correctly. All right, you don't have to write down those three, but I just want to let you know we're going to talk about the three Pitot-Static System instruments. We're going to talk about them one at a time. Actually, they're all connected together. In fact, here we go. This would actually be a pretty good diagram to draw, and I'm going to draw it very similar to if we had an altimeter and we had a vertical speed indicator, and they kept calling it ASI. I'm just going to call it airspeed. Now, what we'll probably do is 2 minutes before class is out, we're going to leave our stuff, and I'm going to go show you on an airplane a pitot tube and a static port. But static means not moving. So the air that's touching or going into this static port, little hole on the side of the airplane, the air isn't getting pushed in and the air is not getting sucked out. It's static. The air isn't moving. All it's doing is measuring what is the pressure on the outside of the airplane. The pitot tube, on the other hand, on the far left of this diagram, the pitot tube is pointing straight ahead, and as the airplane moves forward, air is going to get rammed into it. The video called it dynamic pressure. I like to call it ram pressure. So as the aircraft is moving, or let's talk about before the airplane is moving, air is applying some pressure inside of the pitot tube. So the airspeed indicator, it may read 0, because the pressure coming in from the static port and the pressure coming in from the pitot tube are the same. So airspeed is really the pitot pressure, minus the static pressure. In this case right here, if the pitot pressure is 14.7 and the static pressure is 14.7, I know this is going to be a really tough math problem here. Can anybody tell me without using their calculator, what's 14.7 minus 14.7? 0. Okay. So when no air is being pushed into the pitot tube, we still have static pressure inside the pitot tube. But it's not greater, it's not bigger than the air being pushed inside the static port. But as we start moving, and we start shoving air in here, that is, we ram air into there, the static pressure is still in there, but now we're ramming more air in here. So the air pressure inside the pitot tube when we're moving is really ram plus static. So that means that this formula over here, pitot minus static, pitot is really ram plus static. And then, of course, the static is coming down here, minus static. So just for fun, we'll say that static is still 14.7. And we'll just say for fun, at 50 knots indicated airspeed, the ram is 3 pounds per square inch. So this one's really tough again. So we have 3 plus 14.7 minus 14.7. Is this one really tough? I know it's tough. If you have to get out your calculator, it's all right. We end up with 3 psi. Because 3 plus 14.7 is 17.7, 17.7 minus 14. You'll notice here that effectively the static pressures are canceling it out, so that actually equals ram. So you could argue what the airspeed indicator is telling you is how much pressure is going into the pitot tube that is above pressure. It's doing a mathematical calculation for us. It's just doing it mechanically. It's measuring two pressures, and it's subtracting one from the other. And it's literally, it's a mechanical subtraction machine, and it senses two pressures. So did I lose anybody there? Okay, so there, this diagram, the reason I wanted to draw this diagram is not so I could have all that stuff. Yeah, instead of label, that's a good point there, Rodrigo, is that it's the airspeed indicator is not labeled in pounds per square inch. It's labeled in knots indicated airspeed. Whoops, I can't draw with an eraser. It's labeled in knots indicated airspeed. So whatever, if 3 psi, and I made up these numbers, but if 3 psi equals 50 knots, the gauge reads 50 knots. It doesn't read in pounds per square inch. Because what we want as pilots is something we can use and say, oh, that's how fast I'm going. And say, oh, I'm going 3 psi ram air pressure fast. That doesn't really help us. If I said I was going 50 miles an hour, that helps us. Does anybody remember the difference between miles per hour and nautical miles per hour or knots? No, it's a 15% difference. 1 statute mile per hour. I'm putting in statute here because that's what we use in the United States, equals 1 knot. 1 point, you know what? I did that incorrectly. Let me try again. A knot is 15% greater. 1 knot equals 1.15 mile per hour. So if you're in your car and you're doing 115 miles per hour and the speedometer is accurate, you're doing 100 knots. And if you're going that fast and you're not on a racetrack, you're violating state law, I think, in every state. Did they change the laws back in Montana and or Nevada, if you're out in the clear and it's a nice day and nobody's on the road, you can go as fast as is safe. I'm not that worried about it. My car, if I went 115 miles an hour in my car, it would not be safe. It was not designed to go 115 miles an hour. All right, what I wanted you to get out of this diagram, well, now that I've gotten rid of it, so over here we have airspeed. Was the middle one VSI or altitude? Is that you'll notice the VSI only uses static pressure. The altimeter only uses static pressure, but the airspeed indicator uses static and pitot pressure. That's really what I wanted you to get out of this, but darn it if I didn't have to start talking. Anybody got any questions there? Yes, Brian. You go to the restroom whenever you want, as long as you understand that I'm not going to stop giving away answers to the test while you're gone. So if you can shut that door behind you, I'm going to give away the first 10 questions. I already gave away the first 10. Today is answers for 11 through 20. Okay, first gauge we're going to talk about a lot is altimeter. And if you recall from the video yesterday, I know you may not recall, because it was going pretty fast, is there was a lot of different, I don't know why it's going like that, because that's not the order I wanted. I want to talk about MSL first. MSL is an abbreviation for mean sea level. But as pilots, we talk about it MSL. Most of the time, you're going to set those little numbers in the window on the airspeed or on the altimeter so that it is set correctly and the altimeter reads MSL. Another word for this is somebody's going to say true altitude. And true altitude effectively is what is your real live height above sea level, not above the ground. But the only way you can get your true altitude on your altimeter is if you set the correct setting in the altimeter. So I'll give 2 examples. Let's say you go out to Reedley International Airport. You know what? Let's go to Selma International Airport. You go to Selma International Airport, and there's nothing there to tell you 29.4 or 27.72. Guess what you do? You spin the knob, so on that Colesman window, it reads the airport elevation of Selma. Let's make up a number. We'll say Selma is 400 feet. Altimeter. Whatever that altimeter setting. You know you're perfect at that point. Your true altitude is 400 feet. Your altitude above mean sea level is 400 feet. Pilots don't usually talk about true altitude. They usually talk about altitude MSL and altitude AGL, and we'll get to AGL here shortly. So that's one way to set your altimeter. If you're at a location and you don't have, there's no way to get that number, you just set your altimeter till it reads the elevation of the airport you are. Now if you go to Fresno International Airport, actually technically Fresno Yosemite International Airport, back in my day it was called Fresno Air Terminal, 3-letter designator was FAT. And you do not have to overweight the pilot to fly there. And we'll talk about, in any case, they have what's called ATIS. You don't have to write this down, but ATIS is Automatic Terminal Information Service. And there's somebody at the airport in the control tower that is measuring the barometric pressure, and they put it on a radio frequency, and you click your radio over to it, and it tells you altimeter setting 2, 9, or 7. And rotate the knob and it says 2, 9, or 9, or 7, and then you look at the altimeter to see is it close to the airport elevation. And I'll make up a number. We'll just say the airport elevation in Fresno is 350. You crank in 29.97 or whatever you said, and you look at your altimeter, and it needs to be plus or minus 75 feet of whatever the airport elevation is. So you look at the airport elevation, it says 350. You look at your altimeter, it says 360. You're within 10. That's easily better than within 75, and you go, sweet, my altimeter's working correctly. You're going to do that check if you're at Selma International. Interestingly enough, at Reedley International, they have a little weather station, and it records the pressure, and it actually is a computerized voice spitting it out, and you can actually crank the radio over and listen to it in advance. So I'm going to say it again. MSL stands for mean sea level. That's your true altitude, and this is your height above sea level. And mean is a different word for average. Because if you've ever been to the ocean, because of tide, some days the ocean is 2, 3, 4, 5, 6, 7, 8, 9, 10 feet higher than it is on other days. We're talking about average sea level. And that's what's on your altimeter. So I'm actually going to go straight over to indicated. Indicated altitude is whatever it shows on your altimeter, even if you set it wrong. It's whatever your altimeter says you are, even if you set the pressure in the inches of mercury incorrectly. So our hope is always be exactly the really, really, really close to mean sea level. If you're going to reset aviation regulation, it says if you go fly around, you say go across country, and let's say you're going to fly 300 miles away. Just say for fun, we're going to fly to Barstow, because that is a hopping town. Anybody ever driven through Barstow? Yeah, would you say it's a hopping town? Yeah, what's the definition of hopping? It's exciting, right? They got everything going on there. They got nightclubs. Actually, all they have is a McDonald's and about 27 gas stations. Starbucks. They got a Starbucks. Actually, they have They have a Popeyes. You can get Cajun fried franchise Cajun fried chicken there. In any case, let's say Barstow's 300 miles away, and you're going to fly your Cessna 152 out there. If it's 300 nautical miles away, if you set your altimeter so it's correct, we'll say you're taking off out of Selma International Airport. You set it to 400 feet. Aviation regulations say that as you're flying along on a flight, your altimeter has to be set to the correct altimeter setting of a station that's within 100 nautical miles of wherever you are. So while I'm flying in flight, I'm probably going to, in my 150, I can't get straight over the Sierras. I'm probably going to fly down to Bakersfield and then turn slightly to Tehachapi's, and then also stay out of the restricted airspace around Edwards Air Force Base. But what you could do is you can look up and say, oh, Bakersfield, that's about 90 miles away. When I'm about halfway between Selma and Bakersfield, you tune in a frequency of Bakersfield Airport, and somebody there has a pre-recorded, and it tells you what the altimeter setting is, and you set it. Yes, question. You look it up. There's a book. They used to call it the Airport Facility Directory. Now it's the Digital Chart Supplement. But it's a book, and you can just go and look up Bakersfield. There's like a book that's got all this data of all the airports in the United States. Well, actually, it's several books for the United States, but there's one that's got California in it. There's a lot of airports. You just flip through it. Oh, Bakersfield. You crank it in. You might be on an aeronautical chart that you're flying along. The ATIS, the Automatic Terminal Information Service, will be there. You can also call a weather person that used to be an FAA to Lockheed Martin. Somebody, and they got a computer in front of them. They'll tell you anything that you want to know about the weather, including your altimeter setting. So let's say, you pass Bakersfield, you're going along, there's another airport, there's William J. Fox Field down by Mojave. Halfway between Bakersfield and there, you listen to their ATIS and you crank it. But so the majority of the time, in fact, all of the time, your indicated altitude is going to be really, really, really close to mean sea level. The only time it's going to be off even a little is when you fly for a long distance and you haven't updated that little setting on your altimeter. Okay, AGL stands for above ground level. Now I put these two first, MSL and AGL, because those are the two that you use all the darn time. We're going to use the other ones some a bit. We pretty much never talk about indicated altitude because we're great pilots and we always set our altimeters often enough that our indicated altitude is really, really, really close, and close enough we don't care. It's really MSL. But above ground level, that's something you're going to have to figure out yourself. Because above ground level is how high are you above the dirt below you. If you go out to Reedley International and you look down at the runway at Reedley International, there is a mountain over here. And there's a little tiny R on this side, and there's an S on that side. And if you're flying around in the traffic pattern, you actually get kind of close to the mountain. And the height of that mountain is 1,700 MSL. Everything on the charts are in MSL because your altimeter is set to MSL. So if you look at this thing right there, you'll notice that it says it's about 1,700 feet MSL. Well, you could fly. What that means is if I want to fly over the top of that, I better be higher than 1,700 feet on my altimeter. Let's say it's 1,800 feet. My altimeter says 1,800 feet, and I'm right smack over the top of the mountain. What is my altitude? AGL. 1 foot above ground level. That's 1 foot. If Reedley International Airport is the airport elevation is 380 feet, and the traffic pattern altitude is 1,000 feet AGL, and that's very typical at most of the airports in the United States. The traffic pattern altitude is 1,000 feet above the airport elevation. What is our altimeter going to say when we're on this traffic pattern? This 380 is the height of the airport above mean sea level. And our altimeter reads mean sea level. How high does our altimeter need to read if we're on this traffic pattern? Okay, if we're at 0, we're 380 feet below the dirt. I hate flying below the dirt because it doesn't work very well. It slows you down really fast. Okay, I'll give you a hint. We want to be 1,000 feet above the ground. If the ground is at 380 feet and we want to be 1,000 feet above that, how high what does the altimeter need to say? 1,380. So we need to be 1,380 MSL, which guess what? That's what our altimeter reads pretty much all the time. So as a pilot, you're going to do this over and over and over again. You're going to look at the airport elevation, and you're going to look in the digital chart supplement, and it may say nothing about the traffic pattern altitude. If it doesn't say anything, pow, it's automatically 1,000 feet. So that means when I'm 5-10 miles away from the airport, I'm going to start descending down to 1,380 feet on my altimeter. And I don't want to have to look that way or that way to see the airplanes. I want to be able to just look right out there because everybody else is at 1,380 feet. It makes it safer because you know where the other airplanes are. You're going to look for them. So that's also very important when we're flying around in the mountains. Let's say we're flying around in the mountains instead of 17. So we're in the Andes in Peru because there's no 17,000-foot mountains in the 48. Well, I guess there are Mount Denali's 19. Mount Denali 19,000 in Alaska. So there's a 17,000-foot mountain, and we want to clear it by 2,000 feet. That's pretty much typically, if you're going to fly in mountainous terrain, is to stay at least 2,000 feet above wherever you want. So if we find a 17,000-foot mountain, we're going to need to fly 19,000 feet MSL on our altimeter, but that's only going to give us 2,000 feet AGL above ground level. So in aviation, as a pilot, people are going to say altitude MSL and altitude AGL all the time. Okay, indicated out. We already did indicated altitude. Ka-chink, ka-chink, ka-chink. Pressure altitude. It's when the altimeter is set to 29.92. You'll be flying a pressure altitude. If you set your altimeter to 29.92, your altimeter reads your pressure altitude. Now you may not be, that's probably the wrong altimeter setting. It's probably not correct, because that an altimeter setting could be anywhere from 29.00 to 31.00, and that's just normal weather. If it's really good weather front, it could actually be below 29 or above 31. Hundreds of altimeters. Here, maybe this will help. If you're an airplane in the United States and you go past 18,000 feet, everybody sets their altimeter setting to 29.92, so everyone above 18,000 feet is flying a pressure altitude. Could you imagine in a jet you're going 600 miles an hour? You have to call up or listen and try to read the altimeter every 10 minutes. That would be a big pain. So I don't know how many decades ago they figured this out. They said, you know what, everybody above 18,000 feet, you just set your altimeter to 29.92. And now your altimeter is giving you a pressure altitude. So when I said earlier that almost all the time your altimeter is reading MSL, that's only for us private pilots that are flying below 18,000 feet. If we're flying in a jet or a big turboprop, or actually Cessna 210 out there that doesn't have the prop, it's got a turbocharger on it, it'll go to 20,000 feet. But that pilot, and they could actually, well, to go above that high, you got to have an instrument rating. But everybody up there is flying a pressure altitude. The whole point there is to not hit other points. If you're above 18,000 feet, does it matter if your true altitude is 17,000 or 19,000? Not really. The only time it would make any difference is in case you're really smart, 35,000. Stop worrying about it. Everybody that's in that airspace, and that's, you don't have to write this down yet, but that's called Class A airspace in the United States, is 18,000 feet and higher is Class A airspace, and everybody flies a pressure altitude. A pressure altitude just means your altimeter is flying above a level of pressure, and it's not showing you your altitude above the ground. It's not showing you your altitude above sea level. It's showing you an altitude above a specific pressure. It's actually showing, if you crank in 29.92, it's showing your height above wherever it would be 29.92. So the only time you're ever going to set that, there's actually two times you're going to set this. Once is if you're above 18,000 feet. And the other is if you're at an airport that doesn't have weather reporting capability and you want to be able to figure out the performance of your airplane. You need to figure out what density altitude. You need two things. You need your pressure altitude and you need your... If you could go out to your airplane in 29 altimeter, it's pressure altitude. Let's say it's a hot day at Reedley International. You go out there and you spend 29.92 and it reads 700 feet. And then you look at a temperature gauge and it says it's 29 degrees Celsius. Through that in a chart and it tells you, it says your density altitude is 1,300 feet. So that means your airplane's, even on the runway, even though you're really only 0 feet AGL, even though you're really only 380 feet above sea level, the engine and the airframe is going to act like you're 1,300 feet above sea level. So can the engine produce as much horsepower at 1,300 feet as it does at sea level? No, it's a little bit less. So what do you think is going to happen to the length of your runway? You're going to need a longer runway. And how about to get over that tree at the end of the airport? You're going to wish you had a little more distance. It's not going to climb as fast. So there is a second time where you might set pressure altitude into your altimeter, and that's so you can find out what is the pressure altitude at my airport. I combine that with the temperature, and then I can calculate this last one, density altitude. So I can't overemphasize, we'll be done here shortly. I can't overemphasize the importance of density altitude, and you've already heard effectively the reasons why. Is because not only is the engine horsepower affected by if the air is thin or thick, but the airflow across the wings are different. If we're at a higher altitude and the air is thinner, that is, the air is less dense, will the wings act exactly the same way they did in the thick air at sea level? No, they won't. So I'll give you one example. Let's say we take that Cessna 152 and we put a turbocharger on it. Maintain that 108 horsepower all the way to 18,000 feet. Yeah! I'm going to go into Class A airspace. Woohoo! All right. The wings are not turbocharged. So let's say I want to go into Leadville, Colorado, and the altimeter altitude there is 10,000 feet. We'll say it's a standard hot day. The engine will still be able to produce that 108 horsepower, but the airflow over the wings, it's 10,000 feet density altitude. And the wings getting lift, the wings will generate less lift if the air is less dense. So even if I get the same horsepower, I'm still going to need a longer runway because I have to go faster to get the same lift. So you're going to write this down. Density altitude impacts engine horsepower, and it also impacts the wing getting lift. So this, we're not going to do it today, but we're going to end up before the semester is over is calculating different scenarios based on density altitude and seeing how long of a runway do we need and how high can we climb and how much weight pardon me? It impacts engine horsepower and it impacts how much lift the wing gets. And in both cases, less dense air is worse. And in fact, you might as well write it down because we're still here. Less dense air is typically at higher altitudes and hotter temperatures. I guess there's a third one. It's lower pressures because weather can come in. So if you're at higher density altitude, and this is kind of weird, higher density altitude, 10,000 feet density altitude is higher and worse than 1,000 feet density altitude. But altitude you're at, pressure you're at, and temperature you're at are the three things that are going to impact density altitude. And with that, we're going to go outside and I'm going to show you a pitot tube and a static port. And then we'll dismiss class for 10 minutes.